Howdy ho everyone, my name is Max Joyce. We're here at Physics 2011 with Lab 2 Motion of a Falling Object. Alright, going straight through an overview, we're going to talk about introduction, we're going to talk about dropping paper ball, we're going to talk about a tracker, we're going to talk about a computational model, we're doing a little bit of graphical analysis, and we're going to finish it off with some conclusions. Alright, so introduction, we're talking about two things really, free fall and drag, right? I'm going to go over these a little bit more in depth. Also, we got some equations right there. We got the Newton's second law and the position update formula. All right, going about free fall and drag. So free fall, of course, is an object is dropping with only the force of gravity pulling down on it. So in actuality, like in real life, this is very rare because, of course, we have this thing called air resistance, which we're about to get into. But for part of this example, we're going to only be looking at when our net force is equal to gravity, right? So drag force, it's going to act in the opposite direction of gravity. And it's with that little equation down there that F of drag equals the drag constant times the velocity squared times the unit vector of the velocity. And just make sure that we're noting that if there is no drag, then only gravity is present. That's what I said when we're doing that free fall stuff. All right, so we're talking about Newton's second law, pretty straightforward stuff, relates net force interaction to a change in momentum over some time, and final velocity is dependent on the net force and the amount of time the net force is acting on the system. That's why we got the equation down there at the bottom. All right, so this was our actual video dropping a paper ball. Paper ball is dropped from rest from a meter up in the air. The system, of course, is the paper ball. The surroundings are the earth, but what else is it? It's going to be also the air resistance, and then we're not really going to be looking at this, but actually when the ball hits the ground, it's actually going to be the contact that the ground has on the ball, the paper ball, additionally. All right, so moving on, we're going to look at our force diagram. Force diagrams help visualize force. Of course, there's no friction and applied force in this, so they'll be ignored. Why? Because really we're only looking at the y direction, right? So as you can see, we got the force of gravity there, we got the force of drag there. They're of course going to be opposite directions, but as you'll see, the force of gravity is going to be much larger than the drag force. So really, drag is not going to make that much big of a difference. All right, so this is our tracker model right here. I'm gonna let the video play for itself. You'll see that the tracker is gonna be showing that the ball is dropped, right? If you look to the right, that's gonna be our X position, which we're not really looking at. Bottom, we got the Y position. That's what we're really interested in. You can see that's a nice quadratic shape because, of course, our F net is not 0, our F net is something, so that means our velocity is not going to be constant throughout the motion. So of course we're going to have a quadratic shape when it comes to our position graph, right? So another thing to note is that after the ball hits the floor, which is going to be around the time equals 0.5 seconds, I'm basically going to cut everything off, right? Because that's not really what we're not looking for it after the bounce. We just want to see it in that drop. So for all intents and purposes, we're stopping around that 0.5 mark. All right, going into the computational model, I found that our drag constant was about 0.0266. Now, we did this a little bit of calculations I won't get into here, but looking at that next line of code, we've got to calculate the net force. So, of course, the weight is equal to negative 9.8. The force of drag is equal, once again, to that equation, which is going to be that b value, or negative b value. And then we got the magnitude of the velocity squared, and times the essentially that norm ball velocity is going to be that unit vector. All right, remember that force net is going to be W plus F of D. Okay, so the last thing important about this computational model is going to be the velocity, that little equation I got set up at the bottom. So of course our velocity is not constant, therefore we got to make a little equation. We got this from Newton's second law, right? That velocity update formula, that the final velocity, saying that the initial velocity is 0, is going to equal the the net force divided by the mass times delta t. Of course, our mass here is 1, so we can kind of just ignore it. Just say that the velocity will equal F net times delta t plus whatever velocity we had when we started. So this takes it at each time step, which we found was 0.033, which came straight from the tracker. All right, similarly, our position is going to be updated at a similar time. It's going to be the ball position is going to equal the velocity of the ball times delta t for every single iteration, right? So this is going to update, so we get that quadratic shape. So as you can see in the graph, we got that perfect quadratic shape. So that dark blue line on the top is the tracker. Then we got the F net is force of gravity and the force of drag, and then the bottom one, of course, is just the force of gravity. So as you can see, it took the ball longer to go the 1 meter distance when drag, and in actuality, which makes sense because, of course, drag is acting in the opposite direction than the net force, or than gravity. So we're going to have a longer time. All right, so doing these additional questions really quick. Terminal velocity is the maximum velocity that an object can have, right? None of these models really showed that, but eventually they will show if we dropped it from a high enough distance. Of course, we're going to reach a final velocity very quickly, right? Or excuse me, we're going to reach that max velocity very quickly if we drop it from a high distance. The what if question, the terminal velocity would be the same. However, because we throw it downward, we're going to reach that terminal velocity a bit quicker. So if you're to see that as a velocity versus time graph, of course, you're going to start off with a lot of velocity, but it's going to still level out eventually at that terminal velocity, which means the terminal velocity is once again the velocity which it cannot increase anymore.